we're going to discuss what's known as the cumulative distribution function. So, a really concise, narrowed down description of the probability distribution of a random variable x, either that being discrete or it being continuous. This can be achieved, this description, through its cumulative distribution function. All right, so let's take a look at the definition. So we have the cumulative distribution function, or what we can call the CDF, of a random variable x gives the probability of events of the form x is less than or equal to x for all numbers x. A random variable x is typically denoted by a capital letter, and that capital letter is usually going to be the capital letter F. So in the mathematical notation, the CDF of our random variable x is defined as f, and we'll make it f sub x, right? The subscript is the random variable x of x is equal to p parentheses that random variable x less than or equal to x. All right, so this is how we'll look at the mathematical notation for the CDF of a random variable x. So it's described as this: for all numbers x of the real number line from negative infinity to positive infinity. All right, so when no confusion is possible, the CDF of x will simply just be denoted as, we'll say f x. That is, the subscript x is going to usually be omitted, that little subscript that we have. Starting out with the proposition, the cumulative distribution function f of any, and when we say any, we mean discrete or continuous random variable x, satisfies the following basic properties. So the first property is that it is what's called non-decreasing. It's non-decreasing where we can say that if a is less than or equal to b, then fa is less than or equal to fb. 2 will be that f negative infinity is equal to 0, f positive infinity is equal to 1, and then 3, if a is less than b, then we can say that the probability of x, that random variable being between a and b, is equal to fb minus fa. In our first example, we have the probability mass function of a random variable x is the following. So we have x 1, 2, 3, 4, and then we'll have px, which will be 0.4, 0.3, 0.2, and 0.1. All right, so what are we going to do here? We are told to find the cumulative distribution function f of x. So find the CDF f of x. All right, so let's work through this and get some type of solution. So this given probability mass function, the given probability mass function actually implies that the sample space of X is equal to 1, 2, 3, 4, right? So that Px equals X is equal to Px for X equals 1, and then dot, 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 we'll say to 4, and then that Px equals X is equal to 0 for all other values, right? So all other X values. So the key to finding the CDF is to re-express the cumulative probabilities. So that's what we're looking at, re-expressing the cumulative probabilities. Px less than or equal to X. And we're going to re-express these in terms of the probabilities Px equals X for X in the sample space. So you note first that Px is less than or equal to 1 is equal to Px equals 1, right? This is because X does not take values less than 1. All right, so also Px is less than or equal to 2 is equal to Px is equal to 1, union with X is equal to 2. And this is because if that random variable X is less than or equal to 2, then either X is equal to 1 or the random variable X is equal to 2. All right, so for similar reasons, the probability of random variable X less than or equal to 3 is equal to it being less than or equal to 2 union with it being equal to 3. All right, so using now the additive property of probability, right? The probability of the union of disjoint events equal the sum of their probabilities and the probability mass function of X, we can compute Fx. We can compute Fx for all X. So Fx for all X in Sx. We can do that. All right, so let's go ahead and take a look. We have F1. Let's scroll up a bit. Is equal to P random variable X less than or equal to 1 is equal to P X equals 1, and that's going to be 0.4. Right, and then I'll do F2 is equal to P random variable X is less than or equal to 2 is equal to F1 plus Px equals 2. All right, so that should come to 0.4 plus 0.3 is 0.7. All right, and then the next one, F3, that's going to be equal to P x less than or equal to 3 equals F2 plus P x is equal to 3, random variable. So that gets us the calculation of 0.7 plus 0.2, and that's 0.9. 0.9. All right, and then F4 is equal to P x is less than or equal to 4. So that's going to be equal to F3 plus P x is equal to 4. P x equals 4. Okay, so now that calculation, as you probably already have, right, should be 0.9 plus 0.1, which is equal to 1. All right, so it remains to determine fx for all x values that are not in the sample space, right? Again, the key is to express the cumulative probabilities, all right? The cumulative probabilities p random variable x is less than or equal to x for x not in the sample space in terms of cumulative probabilities um, p x less than or equal to x for x in the sample space. All right, so the end result, and I guess you can call them quick explanations, are we have fx equals 0 for all x less than 1, right? And this is because x, when the variable x is less than or equal to x equals 0, right? And then fx equals 1. I'm sorry, not 1. Fx equals, let's make that f1 equals 0.4. And this is for all x, and this is a little bit different. This is for all x between 1 and 2, right? Between 1 and 2, because x less than or equal to x is equal to x less than or equal to 1. Okay, and then we have fx equals, that's what I did, had f1 up there, f2 is 0.7, and this is for all x, this time x being between 2 and 3. And this is because x is less than, random variable x is less than x is equal to x being less than or equal to 2. Right, and then the next one, fx is equal to, now we have f3, and that's going to be 0.9 for all, this time x being between 3 and 4. 3 and 4. And this is because x less than or equal to x is equal to, this time the random variable being less than or equal to 3. And then we have f of x is equal to f of 4, which is equal to 1, we said. And this is for all where 4 is less than or equal to x, right? And this is because x is less than or equal to x, that random variable is less than or equal to x, is equal to the random variable x being less than or equal to 4. So for this example, the function f of x is plotted in this figure that you see right in front of you. So functions with plots such as the figure that you see are things you might have heard of. They're called step, or sometimes they're called jump functions, step or jump functions.